So I got to kind of get a feel for the manufacturing processes, things that go into it, how it works. So it's pretty cool. So I'm going to share a little bit about what I learned and also just manufacturing processes. So first, what comes to mind when you think of manufacturing? Products. What else? What do y'all think of? Machines, booms? Okay. All right. Well, for me, this is kind of what I think of. I think of gears, I think of metal, think of machinery, think of cars along an assembly line, workers, big warehouses, industry pretty much. Think of conveyor belt pushing out thousands of products. This is kind of how I visually depict it, but now let's define it with something that y'all should be familiar with. The 4 pillars of sustainability. Anyone name one of the pillars? Social. What else? Technical. Okay. Now, let's take technical. How would you define manufacturing from a technical aspect?
Takes a lot of high-end equipment to manufacture stuff.
Okay. So what's going on? What's happening? Take it from the beginning. What goes into a manufacturing process?
Raw materials.
Raw material. And what happens to it?
It goes through a procedure.
Okay, it goes through a procedure. Then what's the end result?
Some form of product.
Some product, right? So you take a raw material and you're transforming it into a product or a desired shape. All right, what else we have? Economic. How would you define manufacturing from an economic aspect? Takes money. What about when you're transforming this raw material into some type of part or product? What do you create? What does a product have that raw material doesn't? Value. Okay, you're taking a raw material and you're turning it into something of value. All right. So we did technical, we did economic, social. What do you think? Jobs. Yep. Go back to this picture. You see workers. Provides jobs. What else? What are you writing with? A pen. Basically everything you're using is manufactured in some way. So it provides products, provides jobs, right? All right. So what about environmental?
Byproducts of your process.
Products. All right. Well, what's happening with the process? What are you starting with?
Raw material.
Raw material. Where does that come from?
The environment.
The environment. Yep. Raw material, byproducts. All right. How do we do it? All right. So this is defining manufacturing from the 4 pillars. There's different ways. It's defined differently in whatever professor you talk to, your textbook you read. If anyone's in Dr. Nagel's 480 class, he defined it as transforming a raw material into a useful product through the least expensive method. So the main point is you're turning a raw material into something of value for the benefit of society. So, all right. Now, how do you transform that material into a product? Right? You have to undergo some type of process. Okay. So the way we are going to define or classify our processes is in 4 groups. We have first primary shaping. So you take a raw material. Let's say you take a slab of metal. It goes through some type of shaping process, and then once this shape is made, it goes through some type of secondary process, whether it's machining, cutting it down, any type of drilling, some type of heat treatment to add characteristics or add value, joining, whether it's combining 2 pieces, and then surface treatment is some type of enhancement at the end before you have your finished product. Now, Dr. Nagel, he classified them in 4 different categories. He had formative processes, which are primarily primary shaping, additive, which is your joining, combining of two or more entities. You have subtractive, which is machining or material removing, and then casting, which is type of shaping. So, primary shaping, basically changing the physical properties of the material through the application of energy. What kind of energy can change these properties? Mechanical? Yeah, I mean, what other kinds of energies can change the physical properties of material? Thermal, mechanical, anything else? Yep. Alright, so basically here, some examples. This is sand casting. Basically involves a liquid metal being poured into a mold, and then it solidifies into the desired shape. This is common for mechanical parts. So if you go back to the car on the first slide, your engine parts, you got your gears, you got the engine head, and a lot of mechanical pieces. And then we have injection molding. This can be either a metal or a polymer. Basically, the material is injected into a mold, which forms a shape. You'll see this for the inner body panels of the car, or blow molding, which is another type of molding. It's what forms your water bottles. Rolling is used for metals. Basically, application of a compressive force to deform the material into desired shape. You'll see that for sheet metal, you see that for I-beams. And over there we've got special. It's using a laser, or thermal properties of a laser to cut out a desired shape of the material. If you've ever seen metal plates with a pattern cut in them, that's what that process will do. So then you form your primary shape, and now let's say you need to meet some kind of tolerances or trim it down. So everyone here has done some type of machining. Can anybody name one that you've done? Milling, lathing, yep, right next door. Heat treatment is often to add value. Metals will often be heat treated to add strength and things like that. Then joining processes. Have something simple as a fastener or a bolt, something to combine two entities. Everybody knows welding, joining of two parts through either heat or pressure. Snap fits. Does anybody have a backpack with a little snap clip? There's that. If you look back at a car, you got your seat belt. You're snapping it into place. And also for joining, we have adhesives. And you look at a brick house. How are bricks held together? Mortar. That's the type of adhesive. And then finally, surface treatment. Applying some type of coating to the product to either extend its product life or add value. A lot of times will make it resistant to corrosion. Polishing, right here you have a mechanical type of polishing where it's very expensive. It's basically to create a fine coating, but there's also chemical polishing, which the way I like to look at it is if you take a bar of soap that's maybe rough on the outside, what happens when you drop it in a tub of water? It gets soft, right? So basically, the outer layer, the boundary layer, is dissolving. It would dissolve quicker than the flatter, thicker layers. That's kind of what chemical polishing is. What happens there? Metallizing is when you take a polymer and you apply a thin metallic coat to the outside of it. Will often either for decorative purposes, insulation, and then let's see, painting. You know, what color do you want your car to be? You know, often aesthetics can also be corrosion resistant. All right. So now we'll focus in on some primary shaping examples. Sand casting, like I said, taking a bulk material, pouring it into a mold, and then where it will solidify and cool. So what's happening here is you got this shape, this is the desired shape that you want. Does anybody know what the riser is for? Anybody familiar with this process? The riser is for is when you pour your material in as a liquid, and as it solidifies, does anyone know what's going to happen? It's going to shrink instead. So as it shrinks, the riser has the excess material and fills it up to prevent any gaps. And then what's also necessary in this process is the air has to be evacuated from it, which for sand casting, actually, the air is just able to lead through the sand. And then, but yeah, so basically we're taking a raw material, we're taking a solid, we're transforming it to a liquid so it can be molded into a new shape. So looking at this process and thinking like an engineer, when you're selecting a process, when you're selecting a material, what are some things that you need to consider when choosing this process? Now you know what goes into it. When you're looking at material, you're looking at process, what do you need to consider? Melting temperature, so thermal properties. What else? So you've melted it, so you've taken it from a solid to a liquid. Okay, so you have a liquid. Now you have to pour it into this mold. So what happens if you pour too much and it overflows? You gotta cut off the excess. Well, yeah, you're wasting material, right? So you need to know, exactly how much you need to pour. So now we're talking about fluids. Who's in thermal fluids? All right. So what are some things you need to know about pouring? I don't think anyone, well, unless you've already completed thermo. Anyone heard of Bernoulli's equation? Okay. So what are some things that go into that you need to know?
Viscosity, density,
Pressure.
I forget the rest of it.
Yeah. Basic pressure, velocity. You need to know your head loss. Basically, you need to calculate the flow to ensure you're maximizing the material so you don't get any waste. All right. So we've converted solid to liquid. We've poured it into the mold. Now what happens? Okay, so what properties do you need to look at as it's solidifying? Alright, what you're eventually going to be learning in the next couple weeks is about phase diagrams. The different phases of the material based on temperature and composition. So that's something you need to take into account. And then also, you're forgetting one of the main things everybody likes to focus on is the mechanical properties. Right, so you have your raw material. Let's say you're telling your boss that you have stainless steel martensitic 304L annealed, and it has a Young's modulus of 29 gigapascals. All right. Well, now it undergoes this process. It's melted. It's reformed. Does it still have that strength? What are the changes it undergoes through this process? So, I think I got it all. Things to consider when choosing processes, choosing materials. Here's some examples of some materials that were sand casted. A lot of gears, which will also undergo some type of secondary process to meet tolerances, especially for gears. So we've created our gear, we've created our metal piece. Now it's time to ship it to the car manufacturer so it can be implemented in the car. So we have to have a way to ship it or package it, some type of encasing to put in it. So what do you think of, what material family do you think of when you think of packaging? Okay, polymers. So now we'll get into a process called thermoforming. It's a process used for polymers. But before I explain to you, who can name 3 types of polymers?
We said thermoplastic glass.
Yeah. Okay. Now let's break it down even more. Who can name the 5 levels of structure for a material?
I think we missed that day.
Gotta start even smaller. Electron, atomic, molecular, micromacro. Right? Easy stuff. Okay, so let's focus in on the molecular. So, we talked a little bit. I've been told about the molecular structure of polymers. Does anyone know anything about the molecular structure?
It's like meatballs with spaghetti coming out of them.
Yeah. All right. So, thermoplastic. What type of molecular structure?
All spaghetti.
Okay. What about thermosets? Okay. What about the elastomers? Okay. What's the difference between the
The amount of thermocouples.
Okay, so for this process, only one material, one type of polymer can be used, because what happens is in thermoforming, a sheet of polymer is heated and is lowered into a mold cavity and is deformed, right? So only one type of polymer can be heated and deformed, and that goes down to the molecular structure. So thermoplastics, thermoplastic sheet is heated, and then as visual, it's lowered into this mold cavity, and the vacuum sucks it down against the mold, which allows it to cool and solidify. Now, there's 3 different types of thermoforming. This is vacuum. There's also pressure thermoforming, where the pressure change on top projects it down into the mold, as well as mechanical thermoforming, which I actually got to tour a thermoforming plant over the summer through my internship, which did mechanical thermoforming, and it's pretty cool because this happens, it happens very quickly. So thermosets and elastomers cannot be used for this process because of their cross-linked molecular structure, so they cannot be heated and deformed. Some examples of thermoplastics used for this process: polystyrene, styrofoam, PET. I got this. I had to buy a calculator for the FE yesterday, and I was preparing this, and I realized I was holding something that was thermoformed. So I'm sure everybody's seen some type of encasing, or had struggled to open it with something. I know these are a pain in the butt. So that's PET, and you have acrylic or your bathtubs. Those are thermoformed. So once again, as we did for sandcasting, what are some things that need to be considered when choosing this process? Thermal properties, right? Because we're not trying to melt it, but we're trying to heat it so it's deformed. What else? Mechanical properties. Yep, same thing. Now, what else? What did we talk about? Structure. So material, right? You can't. If your material is a thermoset, you can't use thermoforming, right? So you need to know your material type, thermal properties, mechanical properties, and again for the mechanical properties, you need to understand how your process, what effect the process is going to have on the material, on the properties of the material. So here's some examples. Something as small as a little plastic encasing for a package, or something as large as a bathtub can be used for this process. So now we've kind of talked about some different processes. Now, how do you go about selecting a process for the material you've chosen? Okay. Now, everyone's kind of gone through material selection process. Now, what are the 4 things you have to define in the beginning? 4 things you have to identify. I know you know this. I graded your homework. I'll give you a hint. What does the material have to do?
Is it being useful?
Close was function. Didn't identify a function, right? Then what comes next? Okay, yeah. Similar, yeah. All right, so we have our function, and we have our constraints. These look familiar? Constraints. We have our objective and our free variables, right? This is what you do for the material selection process, right? You're going through trying to identify what your material needs. So we're going to use the same process to select a process. And so our function, what does the process do? Constraints, what are the limits of it? Objective, often to minimize cost or maximize quality. And then your free variables. And now, so you will go through this process for your material selection, decide on your materials, and now you will repeat this process for material process, if that makes sense. So you go through it twice. So that was called translating your design requirements, right? So what comes after that phase? You've identified everything. Now what do you need to do?
Well, when you start with the process, you pick the process, and you already selected the product, and there's a process, and it's just up to you doing some more analysis for cost and going on with that.
Well, you've identified the constraints of your process, but you haven't chosen one yet, right? So you identify your constraints. Now you have all the processes out there. So you need to narrow down what processes can be used for the constraints you've established, right? Process we call screening, right? This is also what you go through with your material selection. And you're going to do this again with your process selection. So you've identified all your needs. You screen them. You eliminate the processes that cannot produce what you, so let's say for a product, it has to be a mass between 10 and 15 kilograms, right? Well, if there's a process that can only create something smaller or something larger, that process cannot be used. So that's basically what we're doing in screening, eliminating processes that cannot do the job. That will narrow us down to a handful of processes, which we will rank based on our objectives. So if we wanted to minimize cost, so let's say we're left with 5 different processes. Now we need to decide which ones will meet the objective or minimize costs the best. Right? And to do this, you need to seek documentation, figure out what has worked in the past, what has not worked. So, as I said, screening, you eliminate processes. So after you define material requirements, define your process requirements, you use them, and you begin narrowing down your processes. So now we're going to do an example, if you would please pull out your computers with CES. So you're an engineer, and you've been given by your boss, they're going to say, we have a CD case, all right? It's a thermoplastic polystyrene, and we need a process to manufacture this material to make a CD case, right? So a thermoplastic CD case. So what do we need to identify? What do we need to define when we're choosing a process? Yeah. All right. So what's the function?
So hold a CD.
Hold a CD. Protect the CD. All right. So what's next? We have our function. What's after the function? Constraints. All right. What are some constraints? And we don't need numbers, but what are some general constraints?
Size.
Size. All right. Cost. What else?
You said you wanted to use that general process on it, so you need a thermoplastic.
Okay, so we got material. What else? What about, think about from a quality aspect. Okay, durability, and also, you want it to close? You want it to pop open all the time, or do you not be able to close it? You know, so talking like tolerances, things like that. Durability. notice in these constraints, you have what we call it your technical constraints, right? It needs to be a certain mass. Okay, you don't want a huge CD case. You know, it needs to be a certain mass. It needs to be a certain size. It needs to be a certain material, right? Certain shape, certain geometry. But then think of something like tolerances. Now that's a quality constraint, right? Because doesn't technically need to be tolerances, but for quality it does. And also we have cost, which is an economic constraint. So we define our constraints. So what else do we need? So objective?
Yeah.
So what do we want our objective to be for the process?
Minimize cost.
Okay, minimize cost. Alright, let's see how we do. Alright, we minimize cost. We have our constraints. So these, for this situation, these numbers are provided to us, right? So our process needs to create a CD with these specifications, okay? So we have this. So we're going to go into CES. Now, who has gone through the screening process on CES with material selection? The limits, the tree function. Is anyone familiar with that? All right, well, we're going to do that for, instead of the material universe, we're going to do the process universe. So if you pull up CES and say level 2, would be good. All right, you're going to go up to the select tab. Is everyone following so far? Select tab. Okay, and now you want to create a limit. Okay, so click the limit button. Actually, excuse me, first you need to set up in the drop down arrow on the left. Once you go to select. Oh, sorry. Here, I'll pull it up and show you. Oh, I see. So for CES, we're going to go into level 2. Alright, so we have CES. Now right here, we want to select. So now we have our now we're in the select tab. So first go to select from. We want to go to the process universe, and we want to go to shaping, because we're trying to shape this material. Okay, so we open up process universe for shaping. So now we want to go to create a limit. Everybody click the limit, and you're going to see some tabs up here in the middle. So now you're going to go through, and you're going to input those constraints that you were just given. So I'll put those back up. So in that limit window, input these constraints. I'll give you a few minutes to do that, and just let me know if you're lost or need help. Go up to tool, options. Oh yeah, shoot. Everyone's following? Yes. Put in the constraints that you know. So you're going to be leaving some areas blank, because these are the constraints that you were given. Everybody following so far? something like batch size for right now, it's not as critical.
Is the minimum section range of section thickness?
I believe so. Yeah. Okay, and then also, what's not as clear up here is we're looking for a primary shaping process. So under the process characteristics, there will be some check boxes, and you want to check the primary shaping process if you haven't done so.
For the roughness, to make just pin one and ignore the A, B, and C check boxes.
Yeah. How are we going?
Where's minimum section?
Minimum section is the range of section thickness. Yeah, when you're done, hit apply. Does anybody still need these up? Okay, so we did our limit. Now, has anyone used the tree function before? Knows how to use that? Alright, so we're going to go to tree. Now, we're in the process universe, so it's going to come up with process. So go to this drop down screen here, drop down menu, and you want to select material universe. Because we were looking at just thermoplastics, right? That's what was identified. So you want to go to polymers, and you want to select just thermoplastics. Just double click thermoplastic. Even though there's a drop down, you should just double click it, and it will come up. How's everyone coming? Is everybody able to create a tree?
You should have. Have you already set it on there? Mass and range?
Okay, so you've done your tree, you've done your limit. Has anyone not gotten that far? Alright. So now if you look at the bottom left window, it will show you the material or the processes. You screen your processes and these are what's left. Right? I have only injection molding. What does everyone else have? Injection. Alright. So this made it a little easy. There's no ranking involved.
You should have all three.
Does everybody have injection molding?
Okay.
Did you fill in all the constraints? Oh, okay. So that's your tree. So you said that. Alright, go back here.
At least I have it.
And that's in my.
Yes, because I put it on a comma. Can I do that? What else?
Okay, does everybody have?
No, I don't know.
Do you have them both? Okay. Oh, go to your tree. Right click. Okay, now go to the drop down, materials first. Go to folder. Okay, you can see you have all the polymers. You need to leave that one. That'll be good. Alright, is everybody good? Alright, so we just went through the screening process to narrow down to a process, right? So say if we were to do this and came up with 3 different processes, we would have to look into those processes, research them, figure out how they work, what are their disadvantages and what are their advantages, and rank them to decide which process would be best. So this is how to go through the screening process in CES. Now I'm going to show you another way to do this. For your homework in the reading, it explains kind of a manual process to go through. So basically, we're going to go through each of our constraints using tables that will be in your book. They basically do the exact same thing. So we know it's a thermoplastic. So you have this table, look at the thermoplastic column, and you have 8 options for processes that can be used, right? So what you would do is, you would write down those 8 processes. So those are your options so far. Now you take your next constraint, and that's to be a mass between 20 and 35 grams. So now you look at the mass table. You find 20 and 35 grams, and you see which polymer shaping processes fall in here, right? You have injection molding, blow molding, thermoforming, polymer casting. So now whatever processes don't appear there, we would cross those off because they can't be used. Specification. Section thickness, same thing. Use the table and find your process, eliminate what cannot be used. Same thing with the shape. And just narrowing down the processes each time. Just scratch them off your list. For tolerance. Let me know if anyone has questions on reading these tables, because they're all in your book, and it kind of explains how to read them.
In the book he's talking about is the PDF that's going to be on Blackboard.
Yes. Yeah. Which is what you're going with. Roughness. And then, based off of these tables, it comes up with injection molding and compression molding. So now, we have 2 options that need to be ranked, right? So, based off our objective to minimize costs, looking at these 2 processes, what would you choose to meet that objective?
injection molding.
Why?
Because the CES software chose that. Assuming it was cheaper.
Okay,
Probably doesn't have compression molding, does it?
it does. The CES is brand new, or as far as years for the book. I know it was at least a year or two old. So things change. But the answer is you most likely don't know, right? That's where the documentation part comes in. You find out what these processes have been used for in the past. You know, what has worked, what has not worked. Okay? What is the cost of each process? So if you're presenting the material you've chosen to your boss, and you say, we've identified 2 processes that can be used. They're going to say, well, which process can be used? What's good about it? You know, can we use the process that we have in the facility? You know, what is the waste involved? Things like that. So you need to know about the process you're choosing, why you chose it. You know, what's good about it, what's bad about it. So let's say you say, all right, for this material we've chosen compression molding because injection molding, while it's commonly used for this type of material and it's more efficient, it's much more expensive than compression molding. Say compression molding is already done in this facility, so it would not require additional equipment. So basically, we've given you this material, we've given you this process we feel is the best combination to produce your product, right? So you've answered their questions, you know, of what process will work and why, right? You need to know what goes into it so you can justify, right? So as we break it down and analyze it, you know, why we are choosing the process, you need to take a step back and think about what's going into the process. So let's take a manufacturing process. What are the outputs?
The product and waste.
Product and waste. All right, so those are the outputs. Now what goes into a manufacturing process to produce that?
Raw materials.
Materials.
And energy.
Energy. What else?
Maybe labor.
Labor. What was that? What else? What else?
Money.
Money. Anything else? Alright. So you need to think about all the inputs that are going into this process that produces this product, right? So when you start breaking it down like this, you start thinking about the life cycle that your product's going to undergo, right? You take your raw materials, take everything else that goes into it. You're doing some kind of process that produces a product. Now what? Now where does it go? Okay? So let's say back on my first slide, you saw a conveyor belt with glass bottles. All right. So who knows what's glass made of? What goes into glass?
Sand.
Sorry? Sand. Okay. So silica, which comes from quartz, which comes from sand. All right. Along with limestone, aluminum oxide, some other components that come together to reach the desired composition. Okay. Different kind of processes can be used, but it's basically melted and formed into the desired shape, right? So, you take all these components, create a bottle, you ship it off. Some little kid gets to throw out a drinking a Coca-Cola out of a glass bottle, recycles it. Now what? Okay, CES has told you your type of glass is recyclable. So is it sustainable? You know, is this a good choice? You know, what makes it recyclable? Okay, when really glass bottles are sometimes made of 100% recycled material. Glass is recycled, it's melted, it's put back into that composition, that the components that I talked about, and it's formed into a new bottle. So when you know that, when you're able to explain how the material is recyclable, how it actually goes into the process and is reused, is a lot more effective than saying, well, the database said it was recyclable, so therefore this is the material we're choosing. So you need to think about the entire life cycle and what goes into it. Yeah. So what I want you to take from this is not only choosing a material that meets the properties that you get.
Megan, pick up the bottle. Does it have a green top?
Yep.
What does that mean?
That it's made from plants.
No.
Isn't it?
No.
It says plant bottle made from plants.
Made from plants?
Yes, that's what it says. 30% of it is.
30% of it. Now, what does that mean then? 30% of that, what does it mean made from plants? What happens to, when you get roses, what happens to them after a while?
They wilt.
And what do you do to them?
Throw them away.
And what happens to them after you throw them away?
It gets,
Guess what?
like, decomposes into the ground.
Decomposes. Okay.
So 30% that will decompose.
What's the difference between that bottle and that bottle?
That one's green.
What else? Is it really green? That's another question. Some of you will get that, some of you won't. What else? What's the difference between that bottle and this bottle? What happens when you throw this bottle away? Generally speaking.
None of it decomposes.
What's that?
None of it decomposes.
Exactly. It goes to a landfill. Then it goes to the ocean.
Gosh, Keith.
Now, what have you been brainwashed for the past 18 to 21 years about plastic? He told you about glass. Which one's more recyclable? That was his whole point. Don't believe the hype. Understand the phenomenon.
All right. So just wrapping up, what I want you to take from this is not only to apply it to your project, but just any problem or design task that you have. To just not only select a material that has properties that meet the needs of the customer, but take a step back and look at the entire life of the product. What goes into it? How is it made? What components go into it being made? And what happens when it's in life? Just things like that to really focus on, just to be able to justify your work, justify what you've chosen. That is all I have, though. Your homework is posted on Blackboard. It'll be up 5:30. And there will be a PDF of the Chapter 18 reading. Homework due next week in lab. Does anyone have any other questions?
Actually, yeah.